So this is question number 44 of the Fields and Capacitors homework booklet. And we're starting off in question number 44 with a graph that shows how the current varies with time as a capacitor is discharged through a 150 ohm resistor. Now, the first thing to say about this question is that it's a real past exam question from about, if I remember rightly, from about 2015. And the exam board made a mistake. What the exam board should have written is a 150 kilo ohm resistor. So actually there was a typing error and the kilo bit was missing. Now what I'll do is have a look at the answers that you should get if we assume that the typing error wasn't there and that this thing actually said 150 kilo ohm resistor. But I'll also outline what the exam board allowed if you just took it as a 150 ohm resistor in the next part of the question. Now, that doesn't really matter for the first part of this question. In the first part of this question, we're asked to explain how the initial charge on the capacitor could be determined from a graph of current against time. Now, the initial charge of the capacitor is the charge on this capacitor when it's fully charged. And when we then connect it to a resistor, all of that charge will then flow away from the negative plate and until the potential difference across these two plates are equal to each other. So if we wanted to know the initial charge on the capacitor, we basically need to know how much charge is stored up on this particular plate altogether. Now, we know that there is a relationship between the charge on the plates and the current that flows, because we know that basically Q is equal to I times T, where T is the amount of time it takes for the capacitor, for example, to discharge. So if we want to know the charge, if we take the current and we multiply it by the time, then current times time, which is the area under this curve, will give us the charge. And so basically all we have to write down is that to find the initial charge on the capacitor, we simply find the area underneath the curve on this particular graph, and that's worth 1 mark. Now this is where the typing error part comes in, because what we're asked to do is we're asked to think about how we would sketch a graph. So we don't have to put numbers onto the graph or anything like that. We're simply asked to sketch it. If instead of it being charged through a 150 kilo ohm resistor, it's now discharged through a 300 kilo ohm resistor. So let's assume that there wasn't a typing error. Let's assume that actually the question actually read that it was a 150 kilo ohm resistor. If we do that, then basically what we're doing is we're now discharging the current through a resistor that's twice as big. Now we're told that it's basically got the same potential difference when it starts, but we've doubled the resistance, and so using our Ohm's law equation, if the potential difference is the same but R doubles, it means that the current halves. So the starting current for this particular, when we discharge the capacitor through this particular resistor, will be half it was when we had a 150 kilo ohm resistor instead. So if we go back to our graph, that's our first marking point. The first mark you get is basically for putting a little cross at half the current compared to what it was when it was being discharged through the 150 kilo ohm resistor. Then there are 2 more marks. One for basically making sure that this is a curve that looks kind of exponential, like that. And then secondly, for making sure that this line eventually kind of meets this line over here. So they kind of join together when the time becomes very big. So you've got 3 marks. One for the starting current being half the initial current when it was discharged through the 150 kilo ohm resistor. One for having an exponential type of curve, and one for basically for making sure that these 2 lines meet together, because after a certain amount of time they will do. If we actually went with this one instead, if we went with a 150 ohm resistor rather than 150 kilo ohm resistor, what that really means is that if we then placed a 300, if we start off with a 150 kilo ohm resistor and got this curve, if we then replace this resistor with a huge resistor, the current to start off with would basically be incredibly small. It would be kind of down here. And in that case, the exam board actually allowed people to have these answers as well. They basically said that you were allowed to start off with an incredibly small current, and it had to be half of the first square. So it had to start off down here. That was the first marking point. The second marking point is that you would get virtually a horizontal line. That was the second marking point that basically meets this curve over here, and if you drew a straight line that met this curve over here, then that was worth 2 marks. So you get 1 mark for an incredibly small current to start off with, and then 2 marks basically for drawing a straight line. Either way is fine, simply because the exam question is actually wrong. Now in part B, there aren't any mistakes in part B. In part B, what we've got is we've got an experiment to show that capacitor does actually store energy. And so what happens is a student charges a capacitor from a battery, and then they discharge it through a small electric motor, and the motor is used to lift a mass vertically upwards. And you may well have seen this when we demonstrated this in class. Now what we're told that the capacitance of this particular capacitor is 0.12 farads. It's charged up to a potential difference of 9 volts, and we raise a weight of 3.5 newtons, and we want to find out the maximum height to which this mass can be raised. So we know that this question is related to energy basically because it tells us that up here. So that kind of gives us a hint that we'll have to use an energy equation. So basically what's going to happen is if we can calculate the energy that's stored in the capacitor, that energy will be used basically to be transferred to the mass, and so this mass is going to be raised up. So the energy that's stored in the capacitor in the end is going to become gravitational potential energy. So we can work out the amount of energy that's stored in our capacitor using this equation here. C is the capacitance of our capacitor, and V is the potential difference across the capacitor. So if we basically put these numbers into here, that's the capacitance. 9 is the potential difference in volts, so we've got 9 squared. And if we calculate this, we get 4.86 volts, and that's the first mark. All of this energy is then going to basically be transferred into gravitational potential energy. So this is going to be equal to mgh. Now mg is the weight of the thing. So the mg is 3.5 newtons. So we end up with this equation here. So we've got 4.86, which is our energy, equals mg, which is 3.5, multiplied by h. And if you wrote that down, you get your second mark. It's then simply a matter of solving this very simple equation, and you get a height of 1.39 meters. And if you do that, you get a third mark. The fourth mark comes from this statement here. So we want to give our final answer to an appropriate number of significant figures. Well, if we look at the significant figures in the question, that's 2 significant figures, that's 2, and that's 2 as well. So we have to give our answer to also 2 significant figures. 1.39 to 2 significant figures is 1.4. So that's our fourth mark for writing this answer down to 2 significant figures. The final part of this question is for giving 2 reasons why this value we calculated before, the 1.4 meters, wouldn't be achieved in practice. In other words, what they're saying is it isn't going to get to 1.4 meters, it'll actually get to a height that's less than that. So there's a number of different answers that you can have. So but we need to be specific. It's no good just saying, oh, energy is lost as heat or energy is lost as sound, because they don't allow sound. What they do allow is this. They allow, first of all, energy is lost through heating in the wires. So they allow that. Or they allow very similar statements such as energy is lost through heating of the circuit, or energy is lost through I squared R heating, which is basically the same thing. The second point, energy is also lost overcoming frictional forces in the motor. You could also have, for example, any other situation that's fine. What you can't have is energy is lost due to sound, energy is lost due to air resistance, or just general energy is lost because the wires have resistance. If you want to say something about wires having resistance, you have to say that then the wire's resistance means that you have heating, and so basically you go back to this point over here. So you have to be very specific again. So that's question number 44 of the Fields and Capacitors homework booklet.